Thank you all for coming. So as he mentioned, I'm going to be talking about the canonical contact structure in the space of non-geodesics of the space-time, and we will talk about how Engel geometry plays a role in this theory. All of what I'm going to talk about today is joint work with Rubio, which you can find in this preprint here. I'm going to spend a substantial amount of the talk about the first part of the title, and then I'm going to jump to Engel geometry, which I think is maybe more interesting, but I wanted to make sure that we get there all on the same page so that we can fully understand. So, come back here. Great. So I'm going to use spacetimes and contact structures. Then we're going to apply the theory to a special case of spacetimes, which are easy enough to be computable, but non-trivial in some sense that I'm going to develop. And we're going to end up talking about Engel geometry and the whole role in the picture. So let's start with very baby steps. Recall that a Lorentz manifold is simply an n-dimensional connected differential manifold together with the with the self-remaining metric that has n-1 positive directions on every point and 1 negative direction. Recall also that any non-zero tangent vector can be classified via how it behaves under the metric, like this, and also that the space of non-space-like the set of non-space-like vectors forms a bundle of solid cones, and that the boundary of these cones are exactly the null or the light-like vectors, which we're going to be interested in. I'm going to denote this bundle of null vectors by letters. So this is the picture to have in mind. This is dimension 2 plus 1, where I have my point x, my Lorentz manifold, I have my cone, and so I have this, everything inside the cone is not space-like, everything on the boundary of the cone is light-like. So this allows us to define where space-time is, which is simply going to be a Lorentz manifold of dimension at least 3, together with a time-like vector field. So I have a vector field defined everywhere, which is time-like. This is not always possible to do, but whenever I can find one of these, I can endow my Lorentz manifold with the structure of space-time. So this choice of a global time-like vector field is equivalent to choosing one of these two heavy cones in a consistent way all over my map. Do we have examples of this? Well, of course, maybe the most basic one is in space-time, where I take Rm and then I take the last coordinate to be negative, and I can take this time-like vector field tangent to the last coordinate. What can I do with spacetimes? Well, there's many things I can do with spacetimes, but one of them is to define the so-called space of null geodesics. So this is a priori only going to be a set, and what I'm going to do is I'm going to take all of my null geodesics in my spacetime, so all of the geodesics which are null tangent vectors at all points, and I'm going to take them inextensible and also unparameterized. So I only care about the image of those geodesics inside of my spacetime. As I said, this is maybe only a set, but what I want is to give this extra structure. And the way I'm going to do this is I'm going to see it as a quotient of some manifold, so that maybe you can endow it with topological structure and maybe even a small structure. So to do this, let me introduce two vector fields. These two vector fields are going to be defined on the tangent bundle of my spacetime. And I'm going to define them via their integral lines. So of course, an integral line to a vector on the tangent bundle is going to be simply a collection of tangent vectors to my spacetime. And the two vector fields I'm going to define are the Euler field on the left and the geodesic spray on the right. These are the integral lines of these vector fields, which go from blue to red. So for instance, for the Euler vector field, what I need to do to get an integral line of the Euler vector field is take a tangent vector of my spacetime and just make it larger. That's going to be a curve in the tangent manifold, and that's going to be, by definition, an integral curve of the Euler spray, of the Euler vector field, sorry. For the geodesic spray, I'm going to do something similar. What I'm going to do is take a geodesic in my spacetime and take the tangent vector field to that geodesic. And that's going to be a curve in the tangent bundle. And that's going to be, by definition, an integral curve of the geodesic spray. Great, so one can think a bit about these things and realize that they are actually tangent to the bundle of future honeycombs. So this C plus denotes the bundle of chosen future hemicone. So out of every cone, I take only one future hemicone, and I see that these two vector fields are actually tangent to this submanifold, and that they form an involution distribution. So by Frobenius integrability theorem, I can actually integrate this distribution, and so it makes sense to consider the space of leaves of the foliation defined by this distribution. So it happens that as a set, I'm going to obtain that the space of leaves is exactly the space of null geodesics. And to give some intuition of why that's the case, maybe you can argue as follows. So we're going to take the bundle of cones. So that's going to take care of the like-like part of my definition of the space of like-like geodesics. I'm going to quotient out by the Euler vector field, which is going to take care of the unparametrized part. So I don't care how fast I'm traveling my geodesics, I don't care about directions. And then when I quotient out by the geodesic spray, what I'm going to do is I'm going to identify directions in different cones for which there's a geodesic going through both of them. So hopefully that will make you agree with me. This space of leads is exactly as I said, the space of null geodesics. So this is going to give me a topology on that space. If I'm lucky enough, meaning if my spacetime is nice enough, this topology is going to be Hausdorff. And again, if I'm lucky enough, this is going to be a smooth manifold. So from now on, I'm only going to work with the case where this space of null geodesics is a smooth manifold. And whenever this happens, so if my spacetime has dimension m, then my tangent manifold has dimension 2m, and the submanifold of codes has dimension 2m minus 1. So when I quotient out by these two vector fields, I'm going to get that the space of null geodesics has dimension 2m. I'll leave this here because it's going to be for the vector. Great, so let's close this chapter for a bit. Let's move to an apparently completely different topic, which are contact structures. So for those of you who have never heard about this topic before, maybe contact geometry is a theory that's on an odd dimensional manifold. So I'm going to take a 2n plus 1 dimensional manifold, and I'm going to define what a contact structure on here is. So contact structure is going to be a codimension 1 distribution, meaning that I take a hyperplane on every tangent space so that it acquires mostly place point. And I'm going to ask it to be maximally non-integrable. That means that whenever I have a submanifold of n, which is tangent to my distribution, it will at most have dimension little n up there. And the way to formalize this is the following. So it is known that a codimension 1 distribution can be expressed at least locally as the kernel of a 1 form. And I'm going to ask if this 1 form satisfies this non-vanishing condition here. And it's going to give me a contact structure. And let me give you an example of this, which is going to come back later on in the talk. So if I take the Riemannian manifold, I can define its unit tangent bundle, which is also going to be a manifold, which is given by the tangent vectors to my manifold, which have length 1. And this is, of course, a bundle over my Riemannian manifold. So in this unit tangent bundle, I can define a canonical contact structure, which I'm going to denote throughout the talk by chi, which is going to be given as follows. So I need to give you a hyperplane on every point of the unit tangent bundle. So I take a tangent vector of unit length, and the way I'm going to define the plane on here is, so well, I can take the orthogonal subspace in here, because I have this metric, and I can lift it to the tangent space in here via the differential of this projection. Let me show you a picture. This is where my Riemannian manifold has dimension 2, so you can see the Riemannian surface in light gray. I have my point x, and I have the tangent space at x in darker gray color. And I take this unit length vector u. So I need to give you a tangent plane to u on the unit tangent bundle. And that's going to be given by 2 directions. So one of the directions is going to be the red one, which is the coordinate tangent to the new fiber I've just added. Right, so I'm depicting this red line on dxs, but it's not on the Riemannian surface, it's on the dimension above. I need more dimensions here. And then the other direction that I'm going to have is the orthogonal subspace to u. So these 2 lines, I'm going to take the direct sum of them in the 3-dimensional space, and this is going to give me a contact plane. Great. So why am I talking about contact structures? And the reason is that whenever I have a space-time, so that its space of null geodesics is a manifold, then this has a canonical contact structure. And the way to define it is via the so-called skies. So skies are going to be subspaces of the space of null geodesics, and I'm going to have one sky for every point of my spacetime. So if I fix a point x of my spacetime, the sky of x is the set of geodesics that contain the point x. And this is going to be at least a subset of my space of null geodesics. Well, it's not only going to be a subset, it's actually going to be a submanifold. And the way to see it is as follows. So recall that we saw the space of null geodesics as a quotient of a bundle of codes. So what I can take is, I can take my point x, for which I want to compute the sky. I can take the cone at x and projectivize it, so quotient up by the Euler vector field. And then this cone is going to become diffeomorphic to the sphere of dimension m-2, where m is the dimension of my spacetime. And then I can quotient up by the geodesic spray, but that's not going to change anything. So the sky of my point x is still going to be diffeomorphic to a sphere of dimension m-2. Great. So why are these useful? So these allow us to compute the canonical contact structure. So I need to give you for every element of the space of null geodesic, so for every null geodesic, I need to give you a hyperplane, right? Which is going to become a contact structure when I do it for every single geodesic. And the way to compute this hyperplane is as follows. I'm going to take 2 points of my geodesic that satisfy some technical condition, which is not so important here. And then I'm going to take their skies, which intersect at gamma by definition, because x and y are both in gamma. And then I'm going to take the direct sum of their tangent spaces. Let me show you again another picture. I have my space of null geodesics. I have my point gamma, which is a geodesic in my spacetime. And then I have 2 points, x and y, whose skies are here depicted in red and blue. They intersect at gamma. I take their tangent spaces, add them up, and I get the contact hyperplane. So this was defined at first by Lowe in his thesis and later work. And he showed that this is actually a contact structure. I'm not going to show that this is a contact structure. This requires some work. But what we can do is recall that these have the dimension m-2 and m-2. So when I add them up, I get dimension 2n-4, which is exactly one less than the dimension of my manifold. So at least it's a codimension 1 distribution. The non-integrability condition, well, it's a bit more difficult. Great. So again, can I give you an example? The answer is yes. Maybe we can go back to Minkowski spacetime. And actually, I think that I can tell you examples that are a bit more difficult. So let's take a spacetime in which I have a so-called Cauchy hypersurface. A Cauchy hypersurface is a hypersurface of my spacetime such that every null geodesic intersects it once and only once. These kind of spaces are called globally hyperbolic. And whenever I have one of these, then I can easily see that my space of null geodesics is going to be the unit tangent bundle of that Cauchy hypersurface, together with the canonical contact structure coming from the fact that it's a unit tangent bundle, as I showed you in some previous slides. So for a Minkowski spacetime, I have a clear Cauchy hypersurface, which is simply taking the last coordinate to be 0. And that's going to be diffeomorphic to r to the m-1. So this is going to be the contact space of null geodesics for Minkowski spacetime. The unit tangent bundle of r to the m-1, together with its canonical contact structure coming from the fact that it's a unit tangent bundle. Wait, so let me give you some other examples. And I mentioned at first that these are non-trivial in some sense. Now I can tell you why they are non-trivial. They are non-trivial because they are not going to be globally hyperbolic. So I will not really have this Cauchy hypersurface, because whenever I have one of these, I already know how it looks like, so it's not too interesting. And actually, that's a lie. They're going to be non-globally hyperbolic, all of them except for one. So well, we're going to start talking about the first one, and then we'll see the others. So okay, these spacetimes are going to be based on a product manifold, and the product is going to be S2 times S1. And I'm going to take S2 to be the spatial part, and then I'm going to take S1 to be the time-like part. But together with this 1/c squared factor here, where c is a positive integer, which I'm going to be able to achieve and produce these different spacetimes for every sim ring of one space. Great, so how do the null geodesics in here look like? Well, this is a very nice product, so I know that the null geodesic is going to split on a geodesic on S2 and then a geodesic on S1, right? So I'm going to have that every geodesic is going to be a great circle in S2, and then just traveling in the S1 at constant speed. And I only need to tell you how fast I'm traveling one with respect to the other, and I will have the whole picture. And since I will only care about unparameterized null geodesics, I can say, okay, well, then I'm setting that I travel the great circle on S2 at unit speed. And then I only need to tell you how fast I'm traveling the time like S1. And one sees, it's pretty easy, that if I want the geodesic to be like, I need to travel the S1 at speed C. So this C is telling me how fast I'm traveling the S1 with respect to the great circle. Great, so here's another picture. This is I'm picking here the case C equal to 4. And what you see here is the great surface is S2 times 0, right? So having this thing is depicted in gray, and then the radial coordinate is giving me the S1 direction. So you can see here, C is equal to 4, so I traveled the S1 4 times when I traveled the great circle once. Great, so let's keep this picture in mind, but change to the case C equal to 1. What's going to happen then? So for C equal to 1, I'm going to travel the S1 at the same speed as the great circle. So I will have that every null geodesic intersects this exactly once, right? This picture is C equal to 4. If I set C equal to 1, I'm going to have only one intersection point. And that means that this is going to be a Cauchy hypersurface. So for C equal to 1, everything's rather easy because I have this Cauchy hypersurface, which is diffeomorphic to the 2 sphere. So my space of null geodesics is simply going to be the unit tangent bundle of the 2 sphere. So what's going to happen for bigger Cs? Then not longer going to have a Cauchy hypersurface, but I still want to somehow take into account the unit tangent bundle of the sphere. And the reason is the following. So for every unit tangent vector to the sphere, I get a unique great circle in blue. And this gives me a unique lift, so a unique like geodesic on the product manifold, which starts at the base point of my tangent. So the slogan here is that every unit tangent vector to the sphere gives me a unique null geodesic on the product manifold. However, I'm going to have different tangent vectors that are going to give me the same null geodesic, right? So here, the 4 tangent vectors in black give me the same geodesic. So what I want is to take the unit tangent bundle of the sphere and portion it out by an action that's going to identify these different tangent vectors. And after thinking a little bit, one realizes that you can define this as an action of ZC, and the action is generated by this element here. It doesn't really matter what it is, it's just generated by this element here, where I see STS2 as inside of the product of two spheres, so that I can write this matrix. Wait, so I have this description, but I want to see it as maybe some manifolds that I already know before. And the answer is that I can actually do this, and the answer that I'm going to get is that these are length spaces. So let me introduce very fastly length spaces. Length spaces are portions of the 3 sphere, and the way to produce them is I take the 3 sphere, I see it inside of C times C, and I take a positive integer, and I consider this ZP action on S3. The portion of S3 by this ZP action is a manifold, and is what I define as the length space P1. So the first thing one realizes is that if I take P to be 2, then I'm simply quotienting up by the antipodal action. And we know that S3 quotient up by the antipodal action is diffeomorphic to the unit tangent bundle of the sphere. So we get it for C equal to 1, the space of null geodesics is the length space to 1. What happens for bigger Cs? Well, for bigger Cs, I'm going to have the following. I'm going to take the Z to C action on S3 that gives me the length space to C1. So this is to C action that you have upstairs. And then I'm going to see that this breaks, so I can break this into an action of ZC of ZC acting on pushing out the Z. So this ZC action breaks in an action of Z2 and then an action of ZC. So this thing here we already have the bundle. So I'm actually going to get that this two pushes that by some action of ZC. Still don't know which one it is. I need to figure it out by this breaking procedure. So one writes this down and you realize that the ZC action that you're looking for is the same as we had in the previous slide. So we recovered that for any C, the space of null geodesics is the length space of C1. Awesome. So we have all of the spaces of null geodesics. What do we want now? They're contact structures. So let's move on to computing the contact structures. Again, for C equal to 1, there's no mystery because I have a Cauchy upper surface, so I'm going to get the canonical contact structure of the unit tangent bundle of S2 coming from the fact that it's a unit tangent. So there's no much mystery, but let me show you how this is proved because it generalizes to bigger Cs. So I'll show you a couple of pictures and then tell you why it generalizes. So let's go back to the blackboard. And let me explicitly tell you what this diffeomorphism looks like. So recall I'm here drawing this is S2 times 0. And I have some light geodesic here. This is the picture I've been showing you. So this diffeomorphism sends gamma to, well, I'm going to take the intersection of gamma with my S2 times 0. And I'm going to take the great circle that gamma projects on. And then I'm going to take the unit tangent vector. So this is going to be Q. This is exactly the diffeomorphism. Okay, so when I intersect, and I take the projection. So here I want to compare two contact structures. So the contact structure on STS2 coming from the fact that it's a space of null geodesics, and also from the fact that it's a unit tangent. And the way I'm going to do this, I'm going to compare them point-wise, because I can do that. So I'm going to take one geodesic, and I'm going to take the corresponding tangent vector, and I'm going to show you the two planes agree. So I'm going to compute the one on the right and show you that it's exactly one plane. And recall that the one on the right, the canonical contact structure in the space of null geodesics, is computed by taking 2 points on my geodesic and then taking the direct sum of the tangent spaces of their skies. So I can take any 2 points x and y I want on this geodesic. And the first that I'm going to take is exactly the intersection of gamma with S2 times 0. So I can take any I want, so this is going to make my life easier. Here you have the same picture I've been drawing. So this is S2 times 0. The geodesic I'm considering is depicted in red. And then the sky of the intersection point is given in blue. So I need to take the tangent space of the sky. But you see that the tangent space here is simply the tangent direction to the fiber of the unit tangent bundle of S2, right? So here I'm going to have a bunch of tangent vectors here based on x, and then I'm going to take the derivative of this curve. So this direction is indeed on the contact plane on the left, because of the picture I showed you at the beginning. Great, so I need to take now another point. And the other point I'm going to take is a point a bit farther away, which up there is given by y, here I did it by gamma of tau, doesn't really matter. It's just a point a bit farther. And the sky of this point is also given by the set of geodesics in blue. And I can see how they intersect this S2 times 0 surface. And I see that they intersect at a circle, and that this circle intersects at x perpendicularly to you. This can be computed, but with the picture it might be easier to see. So I get that the tangent space of this sky is indeed on the contact plane on the left, because it's going to project onto u perpendicular to the orthogonal subspace to u. And so that's it. I get these two contact vectors. And why does this generalize to bigger Cs? Well, for bigger Cs, the only thing I'm going to have is that gamma intersects these hypersurfaces, this type of surface, at more points. But I'm going to have a finite amount of points, so it's going to be straight. So I can take this picture here, I can take it to be small enough so that I can see what happens outside. And so I can run the same exact type. And what I get is that to get the contact structure for bigger Cs, I just need to take the one on here and push it forward by the projection map to the other lenses. Great, so hopefully we now are on the same page of how everything looks like, and I would like now to jump to the Engel part. So if anyone was getting bored, now is the time to come back, because this is the interesting part. Let me start with Engel geometry. So Engel geometry is a theory that's done only on 4 manifolds. And an Engel structure in a 4 manifold is going to be a 2 distribution, so a choice of plane on every tangent space. And I'm going to ask that when I take all of the vector fields in that distribution and I take the bracket, the Lie bracket of them, this generates me a 3 distribution. And then when I run the procedure again, so I take all of the vector fields in the 3 distribution and I take the Lie bracket, this generates me the whole thing. Great, so only by this information, one sees that one can actually find a line field, so a 1 distribution, by this formula here, which is not really important. But what's important is that this gives us a complete flock of the manifold. So only from the information of the 2 distribution D, I obtain a full flock. 1, 2, 3, and then this thing here is going to be really important. I'm going to call it the kernel. I'm going to call this the kernel of my distribution. So this flock comes only from information of this type. And why are these things important in our theory? Well, they are important because I can generate one of these canonically from a 3-dimensional contact manifold, and I can also generate one of these canonically from a 3-dimensional Lorentz manifold. So they're going to be kind of a link between these 2 walls, which are apparently different. So let me show you first how I do the first thing. So I have a 3-dimensional contact manifold, and I want to generate an Engel manifold. So first I need to tell you what the 4-dimensional manifold is going to be. And the way I'm going to do this is I'm going to define it as an S1 bundle over my contact manifold. So I start with my contact manifold here, and then I can define an S1 bundle, which is called SG, by fiber-wise taking the just a circle on every contact plane. So if I have my point here on the contact manifold, I have plane here with the contact plane. So I simply remove the 0 and I quotient that by the action of R plus. So that I get an S1 bundle. And an element in here is going to be simply a pair of the base point I'm looking at, and then an oriented line in here. Right? And what I need now to tell you is what's the Engel plane on this point XR. And the only thing I'm going to take is this line R, which lies in the tangent space of M, and I'm going to lift it up via the differential of this projection. The fact that this is going to be Engel is very related to the fact that this is a contact structure. So the Engel axioms are realized by the fact that this is a contact structure. Again, this is the picture. So I have N, my 3-dimensional contact manifold. I have my point X and the contact plane, and then for a guy XR in here, I just lift up the line R, so the plane is going to be given by 2 directions again. One, the direction tangent to the fiber, and also the direction of R itself. One can ask, what's this thing here then? And it's pretty easy to compute that this thing here is going to be exactly the direction tangent to the fiber I've just added, so to this fiber here. So that means that if I take my manifold, my 4-dimensional manifold, and I quotient out by the kernel, so if I take the space of leaves of the foliation that integrates this distribution, I'm going to get back my 3-dimensional contact manifold because I'm just going to kill the fibers. And what's maybe not so easy to see, but still works out, is that I can recover also a contact structure by taking the push forward of the 3 distribution. So I take this 3 distribution, I push it forward along this projection, and I get back my contact. This procedure here, I'm going to call Cartan deprolongation, because if I call the procedure going from here to here, I call it Cartan prolongation, then this allows me to come back to my original data. So I call it Cartan deprolongation. Awesome. So let's now move to the so-called Lorentz prolongation. So this is going to be a very similar procedure, but starting from a 2+1 Lorentzian manifold. So I take my 2 + 1 Lorentzian manifold, and I need to give you first the 4-dimensional manifold I'm going to work on. And this is simply going to be the projectivization of the cones. So I take my bundle of cones and I projectivize it. This is also going to be an S1 bundle over my 3 manifold. And then here I can do something very similar, which is, well, a point on my 4 manifold is simply going to be a point on my Lorentzian manifold together with a line on the corresponding cone. And then I'm going to simply take this line and lift it upstairs via the differential projection. So again, nice picture here, point on my Lorentzian manifold, cone, direction of my cone, and the 2 directions that are going to generate my Engel plane are the one tangent to the fiber and also the line U. So again, what's this guy here? Well, I'm going to tell you what it is not. It's not the direction tangent to the fiber. It's never the direction tangent to the fiber. So I don't really have a Lorentz prolongation procedure, right? Because if I want to go from PC back to my 3-dimensional manifold, I need to kill by this thing, but this is not something that I can get from the data of my Engel distribution. So the question is, what is it then? And well, we computed that in our paper. We were then told that Yoshiko Mitsumatsu had done something similar, well, had done the same calculation some years ago in a preprint he did not publish. He does it by very different means. We take a more coordinate-like approach, which is kind of tedious, but I think gives a bit more of an idea of the geometry of the whole thing. But what one can compute that this kernel of the Lorentzian prolongation is exactly generated by the geodesics spread. What does this give us? Well, this gives us that we can recover the space of null geodesics, because so if I take BC and I portion that by this kernel, well, BC is exactly just the bundle of cones portioned out by the Euler vector field. And then this thing is exactly the geodesics spray. So by definition, this recovers me the space of null geodesics. And this very much looks like a Cartan prolongation, right? Portioning out by the kernel. So one would hope, okay, well, can I recover then the canonical contact structure via also Cartan prolongation procedure? The answer is yes. So I take this projection here from the 4 manifold to the quotient thing, and I realize that this is exactly the push forward of the 3-dimensional distribution given here by the Engel plane. Great. So what we get is, what we get, and this is the slogan for this part, is we get like a kind of a commutative triangle where I have my space-time. I can define geodesics, but I can also Lorentz prolong it. And Cartan. I get the same thing, right? So you can go this way and I can go that way. Let me give you an example. Let's go back to our favorite product manifold, S times S1 with C equal to 1. And one can show that the Lorentz prolongation is diffeomorphic to this product here, S2 times the unit times model of S2 times S1. And well, one can compute the plug. It's not too important, but for a point UT in this product, this is going to be the flag of the distribution. And well, I can run this Cartan prolongation procedure to see that we get exactly what we were hoping, which is what we computed. Wait, so let me finish with this last thing, which is, okay, now one would like to be able to go back. So if I give you a 3-dimensional contact manifold, can you give me space-time such that the original contact manifold is in space of null geodesics? And well, the sensible thing to look at is, well, I have this thing, so let me try to do something similar, which is let me Cartan prolong this thing to I write a prime here because it has nothing to do with the P. And then, well, I would hope to be able to somehow Lorentz prolong it to go back here. But as I mentioned before, there's no canonical way to Lorentz prolong from this thing here. And what we realized is that, well, well, you need to go a bit further, but you can still do something similar. And what we got is a full characterization of when this guy is the space of null geodesics. So a three-dimensional contact manifold is the space of null geodesics of something, even only if, and I'll try to walk here through this thing. So I'm not going to use this, but I'm going to use another very cute. So I'm going to ask for the existence of another, and you all see what's going on. I'm going to ask for the existence of another four-dimensional Engel manifold, and this gibberish here only means that this cartan belongs here. And I now need some data in order to be able to learn the program. And the data is going to be given by a foliation. So I'm going to ask that in here, there's an oriented foliation by circles that satisfies three things. First one is rather easy. It says that if I have a point in Q, then I have the corresponding circle coming from the foliation. And if I take the tangent direction to the circle plus the kernel of my distribution here, then these two span both. Then I'm also going to ask something. This is rather like a technical thing you need, which is that the foliation is nice enough so that you can take the space of leaves, and that's going to be a manifold, and your projection is going to be a submersion. And then the third thing is maybe the one that's a bit more difficult, but I'm going to try to make it understandable. So if I take a point in N, which is the space of leaves of my foliation, this comes from a circle in here by definition of foliation from space of leaves. So this maps to this point under the projection Q. So I can take one point in here, and this has an Engel plane. We call this point Y. So I have the Engel plane here, Y. And I can ask, okay, what happens if I take the push forward of this plane under the projection? Well, so by point 1, the tangent space to the circle is going to be inside of this plane. And when I take the push forward, that direction is going to be killed. So the answer is that down here, I'm going to have just a line. And this is the line, this is Q star, which lies inside of the tangent space of N. Yeah, this is, I'm taking the push forward of the two plane, I get to a one plane, which is a line. Okay, then what happens if I take another point in here? So this one going to go Z. I have the plane. What happens when I take the push forward? I'm going to get another line in the same tangent space. So what I'm going to ask is that as I go over this leaf, all these lines produce a color. This is the third hypothesis. So this is the space of null geodesics, even only if there exists an Engel structure with a foliation like this one. And whenever this happens, I can Lorentz the program. And the way to Lorentz the program is to take M to be this quotient space, the space of leaves, and to take G to be any metric with this bundle of cones, which always exists. And this gives me back this considered to Lorentz the program. That makes the whole diagram commute. There's a nice thing. Well, so first, what's not so nice is that I need this extra four manifold that comes out of nowhere, and I would like to be able to work with this one, just like I work with the Lorentz prolongation there. Well, this is not always the case, but it is true that this thing cartan that belongs here. So it is enough to find a foliation in here. So it might not always be the case that you can find it, but if you can find such a foliation here, then it works. You don't need this extra four-dimensional manifold. And that's what I'm going to do now. I'm going to finish with an example. That's going to be it. Oh, sorry. Yeah, there's one extra thing, which is that these two are related by a canonical local diffeomorphism that preserves the Engel structure. So that's the best thing you can say about this new thing that pops up. Okay, so let me finish with an example. As I was saying, we're going to take, again, our favorite contact, three-dimensional contact manifold. So I'm going to start here with the unit tangent bundle of S2 together with its canonical contact structure. And this is a nice case because I don't need this four-dimensional manifold. I can work here already. So I'm going to compute its Cartan prolongation, which is diffeomorphic to this product. And I'm also going to go to compute the Engel structure, which is this one here. So for pair UT in this product, I get the whole part. So what do I need? I need this foliation. I need to give you this foliation by circles. So in order to that Cartan different. And the way that I'm going to define it, so I'm going to take for every t in here, I'm going to give you a foliation of circles of this guy here. And that's going to give me a foliation by circles of the whole thing. I'm just going to like slice it in pieces. And the foliation is going to be tangent to the things where this guy is constant. So again, for every point in here, I give you a foliation by circles of this. And then the whole thing together is going to give me a foliation by circles of the format. And this is the picture. It's I don't know, maybe not non-trivial in some sense, or one needs to think about it a little bit. But if I set the S1 coordinate to be pi halves, I'm going to have the trivial foliation by circles of the unit tangent bundle of S2. As t grows bigger, I need to take these kind of circles that grow in radius as t grows, and then to take the tangent vectors that go here. Well, this foliation satisfies 1, 2, 3 in the previous theorem, and one can see that if I take the four manifold and take the space of leaves, I get something diffeomorphic to S2 times 1, which is what I was expecting, and that the bundle of cones is the same as the bundle of cones of the product metric that I was expecting as well. So it works for this case. It's nice and computable, but well, it might not be as nice as computable for other spaces, but we do get a full characterization of this stuff. So that's it. Thank you very much. I'm glad we tried to answer any questions.
I'm going to stop recording.